Hey everybody, today we're going to look at optimization, one of the final topics that we're going to cover in straight up derivatives before we start learning other stuff. So another way we can call this is applied relative extrema or applied mins and maxes. So these can get very real, and this is some of the most useful stuff that people use from calculus. So you might just go, it's derivative word problems. But then that also includes related rates. This is different. So there's a whole set of instructions here that are really helpful, and I'll front end load this really quick. So the first thing that we want to do is we want to find a main equation that we're trying to, what I like to say, optimize. This says maximize or minimize. So there's going to be some formula we have or something that we want to get the most out of or the least out of, and that's what eventually, that's going to be our most important thing, the optimizing formula. Then the second thing it says, use a secondary equation that you're going to have to find that we're then going to be able to alter the original equation, because this first equation is normally going to be in more than one variable. So we're going to try to find it so that we can get it in a single variable so that we can eventually take the derivative of it, because we don't want to take the derivative when there's more than one variable. Second thing, we want to find any implicit domain that we need to pay attention to. So this, we have it here in the middle of the problem, but it's really one of those things that once you get your answer, you can kind of go back and think, okay, does my answer actually make sense? Like if it's like, what's the most number of bricks that we need, and you get negative 12 bricks, it's like, oh, okay, that doesn't make any sense. So then we're going to take the derivative, and we're going to set it equal to 0 to find maxima or minima. All right. And then part 5, this is so important. We want to make sure we actually answer the question. So here we go. Example 1. Find two positive numbers whose sum is 20 and whose product is as large as possible. Whose product is as large as possible. Okay. So the thing that I want to optimize, I want the max product for these two positive numbers. Okay, well, we can call these two positive numbers whatever we want. You could call them x and y, you could call them a and b. I'm going to call them a and b. A times b is equal to my product. I don't know my product. I don't know a, I don't know b. But this is what I eventually want to optimize. I can't take the derivative yet. I'm going to rewrite this p is equal to ab. I like having my essentially like y equals kind of thing over here on the left. We also know that the sum of these two numbers is 20. So we say, well, I know a plus b is equal to 20. And so what we can do is we can go over to this equation and we could sub this in to eliminate one of those two variables. So I'm going to solve for a, I'm going to subtract the b from both sides and get a is equal to 20 minus b. You might want to say negative b plus 20. They're identical, it doesn't matter. So now I can say the product is equal to, instead of writing a, I'm going to write 20 minus b times b, or the product is equal to 20b minus b squared. So that's the product in terms of a single variable. So if I take the derivative right now, if I want to be like really explicit, I can take the derivative of p with respect to b. In my class all the time, we will just represent that as p prime. But we just take the derivative of the right-hand side and we get 20 minus 2b. So the rate of change of the product is equal to this function here. So, or this expression here. So what I can do is I can say, well, when's the rate of change equal to 0? When does the derivative stop changing rate? And that might be a max or a min. So let's see, 20 minus 2b. I need to find out when this equals 0. There's a lot of ways to solve this. I'm going to solve it by adding the 2b to both sides and then dividing by 2 and get b is equal to 10. So there are a few different ways that we can check this. a lot of times in these questions, you get to your answer and you're done. That's going to be the answer. Rarely are we going to run across something where we actually have to test, but just for the sake of argument here, I'm going to show my test. So, wait, it says find two positive numbers. I only found B. I need to go back and I need to find A. So if B is 10, then A is going to equal, I know A plus B is 20, so A plus 10 is 20, so A is also 10. So if I was going to test this, what I would do is I go back to my P prime function and go, okay, so I know that's P prime, and I would do a little, so here's my B values, and here's P prime. So I know I got 10, then I would test like 9, maybe I'd test 11. If I test 9 in P prime, that's 20 minus 18, so it's a positive. Here's 0. If I tried 11, that's a negative. So that means that the product is going up then comes down. So now I'm more convinced that that's a maximum. All right, let's move on to our next example. Example 2, find two positive numbers. So I'm going to switch to A and B this time. Oh wait, no, find two positive number. All right, such that the sum of 1 and 10 more than 3 times the other is 34, such that their product will be maximized. Ooh, big mess. Okay, two positive numbers, we'll call them X and Y. Such that the, let's see, sum of 1 and 10 more than 3 times the other is 34. Okay, let's start with the easy part of this sentence. It says is 34. That means equals 34. Sum of. I see 1 and 10 more than 3 times the other. So sum of this and this, that means put an add between this and this. So I know there's going to be an add here in the middle. There's going to be something over here, and there's going to be something over here. 1. I have had students in the past try to tell me that means the number 1. But then in context, that makes no sense. The sum of the sum of the number 1 and 10 more than 3 times the other. The other is referencing something. The other is referencing this word 1 over here. That means one of the numbers, the other one of the numbers. So one of the numbers, I'm going to call the one number X. 10 more than 3 times the other. So 10 more, that's literally plus 10, than 3 times the other. 3 times the other, that means 3 times that other number, which was y, so 3y. So we gotta do plus 10 and 3y together, which is 3y plus 10. So that's how I got x plus 3y plus 10 is equal to 34. And it says, such that their product will be maximized. So again, product is going to equal AB, well, this time I'm using x and y, so xy. So all I want to do is I want to take this and solve this for one of my variables. I choose to solve for x because there's no coefficient on x. You may choose to solve for y, but then you're going to have to divide by 3 later. Go for it if you want to. So I'm going to subtract the 3y and the 10 from both sides and get x is equal to 24 minus 3y. So then when I go over here and substitute it, I'm going to get product is equal to 24 minus 3y times y. So product is now equal to 24y minus 3y squared. So just like our last question, now I can take the derivative of this, so I can say p prime is equal to 24 minus 6y, set it equal to 0 and solve. So I'll add the 6y to both sides. Actually, I'm going to solve this one differently. You could add the 6y to both sides, or divide by 6 and then get 4. Or I could also, since it's equal 0, I could take the 6 out and get 4 minus y and set it equal to 0 and get y is equal to 4. That was the way I wanted to do the last one too, and that is how I wanted to do this one. For some reason, that just feels quicker to me. Or maybe even you just get here and you notice, they'll cancel when y is 4, so I know that y is 4. But either way, it says find two positive numbers. Well, I know y is 4. So if y is 4, then what is x? Well, let's see. X plus 3y, so 3 times 4, plus 10 is equal to 34. X plus 12 plus 10, x plus 22 is equal to 34. So subtract the 22 from both sides, and I get x is equal to 12. So we got 12 and 4. So if you are not convinced that this is the actual maximum product, again, you can take your y value, go back to your derivative and do a derivative chart. Alternatively, another way to do it is to test the concavity when y is 4. So if we were to test the concavity of this, we know that p prime is equal to 24 minus 6y, right? Well, p double prime, if we take the derivative of that, is equal to negative 6. Oh, the y is even gone. So if we think about what that says about the concavity, remember, concave up looks like a cup, concave down looks like a frown. Positive double prime means concave up, negative means concave down. Since p double prime is always well, that was hard to say. P double prime is always negative 6, therefore p is always concave down. If you think about what concave down looks like, we said it's a frown. A relative extrema, the only place it could occur is at a maximum. Also, it's like a little doggy or something. Here's a droopy. Is droopy too old of a reference? Also, very poor drawing. Sorry, I got distracted. Okay, let's keep going. Oh, I love this one. Oh, you're going to hear me say that way too much with these problems. An open-lidded box. I feel like lidded should have 2 Ds. An open-lidded box is to be made from a sheet of square poster board space with a side length of 20 inches by cutting equal squares from its corners and folding up the sides. So I've got a piece of paper right here. All right, so it's a square now. Okay, so we got a square piece of paper and we said, all right, the side length is 20 inches. All right, so 20 inches here, 20 inches here, 20 inches here, 20 inches here. Okay. Then the problem says, by cutting equal squares from its corners and folding up the sides, what is the maximum volume of the box that can be made using the described process? Okay, so it says we're going to cut out equal squares. All right, so I'm going to use the length of this card to do my squares. Okay, so I'm going to do right there. And right there. Okay, and then I'm going to connect them. All right, so I got my square, and then I use my playing card. It's probably not perfect, but it's close enough. So the main idea is this whole thing is 20. How long is this? Well, we don't know, right? So I'm going to call that X. And this is also X. I used the same side of the playing card for everything. Actually, let me put it here. So if this is the case, how long is this side now? This side is no longer 20. Oh, here's what I mean. Side used to be 20. Now it's 20 minus X. because I just took x away right here. But I'm not just going to take x away right there. I'm also going to take x away over here. So instead of saying I'm taking 20 and removing x from it, we could say I'm taking 20 and removing x from it twice, which is a silly way to say that. I should say 20 minus 2x. They're both totally fine, though. Either one of those is fine. And then I'm going to do that to the other half of the square. All right, so now I've got my pre-box. And so all these sides, this is 20 minus 2x along the top here. And hopefully we can see that this is also going to be 20 minus 2x, because we did the same thing. We did the same thing for all of these. 20 minus 2x, 20 minus 2x, 20 minus 2x, 20 minus 2x, right? And if we were to now take our box and fold along these edges, pretending that everything's perfect here, yoink. Now we've got a little box. And I did all this to kind of help us understand the dimensions of this box. So what do we know? What do we know about this box? Well, it's a rectangle, right? So let's see. What is the maximum volume of the box that can be made using the described process? So let's see. The side length is 20 inches. So maybe we can find out, well, okay, volume. So volume of a rectangular prism is length times width times height. So if I was thinking about this, we know that one dimension of this, show myself, not the camera. We know that one dimension of this is 20 minus 2x. Right, so we could say that we could call it the length if we want. It doesn't matter what you want to call it. So we can say 20 minus 2x. That's that way. Now if I wanted to go that way to get another dimension, that's also 20 minus 2x. And then how tall is it? It is x tall. And so because of that, the volume is equal to that. So I've already kind of taken my second equation and kind of plugged stuff in here. Whoops. Okay, that's fine. So now it comes down to how do you want to differentiate this? And let me show you what I would do if I was drawing it instead. So I would start with a box and I go, oh, I'm cutting x in on each side. Okay. And I know that the length is equal to 20 minus 2x. If I think about, okay, that's 20 minus 2x. And since it's a square, then that's also equal to the width. So that's how I would kind of handle that. And then the height I'm just going to call x, because that, if you think about it, as that folds up, that's going to become the height. So anyway, I think I'd rather FOIL this out than do product rule. So 20 times 20 is 400 minus 40x minus 40x, so that's minus 80x, and then plus 4x squared. All that is still times x. So I'm getting my volume is 4x cubed minus 80x squared plus 400x. So then v prime is 12x squared minus 160x plus 400. So now if I'm going to solve this, I need to set it equal to 0 first. Remember, I'm trying to find any relative maxes or mins to this. Hopefully, since I'm looking for a max in the problem, hopefully this will be a max. So, sorry, got lost in thought. So if I set this equal to 0, 12x squared minus 160x plus 400, I don't believe that they're both divisible by 12, but let's see, because I'd really, really like to, yeah, okay, so not both divisible by 12. Let's try 4, though. If I divide them all by 4, I'll get 3x squared minus 40x plus 100. That's still nicer to deal with. So, factors of 300 that add up to negative 40. I could be here a while. 50 times 60, I believe, is gonna be too much. Yeah, that's thousands. So, oh gosh. It's 10 times 30. And since it needs to be negative 40, it'll be negative 10 and negative 30. So I'm going to use the process of decomposition to factor this. So 3x squared minus 10x minus 30x plus 100. So then I can factor an x out here and get 3x minus 10. I can factor a negative 10 out here and get 3x minus 10. So now I get x minus 10 times 3x minus 10. And so now I'm going to get two of my two critical numbers here. My two critical numbers are 10 and then 3 1/3, or 10/3. So one of those is going to be probably one of those is going to be the answer, but not both. So now I need to do some testing. And I think I would like to do the second derivative test. So 12x squared minus 160x plus 400 is v prime. So if I take the derivative of this and I get v double prime is equal to 24x minus 160. If I try plugging in 10 here, so I do 24 times 10 minus 160, I get 80, which means I have a concave up, looks like a cup. So when x is equal to 10, I've got this. That means that 10 is actually going to minimize my area. And if I look at, let's see, if I look at 10/3, so 24 times 10 over 3 minus 160, I get negative 80. So when x is equal to 10/3, concave down, that means that's going to maximize my area. And so because of that, that tells me that when the height is 10/3, this is going to be what maximizes my, did I say area? Shoot. That's going to be what maximizes my volume. And let's talk about this 10 for another minute. Think about that. If x is 10, what happens to this box? How far is that? That's 20, right? So if you go in 10, go in 10, you just cut the entire box apart. It's gone. You went the whole way. So that goes back to that implicit domain that we talked about before. So 10/3, that's not my answer though. So now I can say volume, okay. So that's going to be 20 minus 2 times 10/3. That happens twice, so I'm just going to write squared on that. And then times 10/3. I need to get going home. It's the end of the day. I need to go let the dog out and then say hi to Mrs. Camfield. So, and then we're going out for a birthday dinner for her sister. So I need to get going. Ugh. All right. I think that's going to be, yeah, all right. So if you feel like it, you can write 16,000 over 27. I'm just going to write that my volume is equal to 592.593 inches cubed. Yeah, if we plugged in this other volume of 10, we would get 0. We'd have a volume of 0. You'd have no box. So, all right. Well, that does it for this video. I will definitely come back and do more of these. We've got a total of, I think, 8 examples. All right. Maybe not. Whatever. Bye.